All right, good afternoon and welcome to ECE 164. Today we're going to talk about small signal models of MOSFETs. All right, so I'd like to start this out by taking a step back and just revisiting something that we've seen before in previous lectures, and that's this common source amplifier. But I want to take this and ask a different question. I want to ask, let's imagine that we had this amplifier and we were trying to design it. What's the limit on the amount of voltage gain that we could get from this circuit? And if we look at the circuit, so we're biasing it with a DC voltage source, we're applying our AC source on top of that, signals coming in the gate. This transistor is then going to convert this voltage into a current. That's why it's a transconductor. And this current gets reconverted back into a voltage at the output, which consists of a DC bias along with our AC signal. Similarly, we have an DC current and an AC current that's flowing through this transistor. And what we're trying to ask is how much gain, how much little V out divided by little V in can I get from the circuit? And we derived this expression that the gain is equal to minus transconductance times R. And this simply comes about from how we set this up, and that's that this transistor really looks like a transconductor. It is taking this voltage, and anytime we wiggle the gate, it's converting that into a corresponding change in the current. So that's the transconductance, or GM in this term. And then this is getting turned into a voltage by this resistance, by the load. So GM times R. And if I start to plug in values that we derived last time for GM, GM is dependent on the biasing conditions, primarily the drain current, the DC drain current, and the overdrive voltage, and this resistance. And if I limit the transistor to operating in saturation, then I know that the voltage drop, ID times R, has to be less than VDD. And that's simply to say that I have enough VDS of this transistor here in order to keep it in saturation. And so this condition is actually not entirely sufficient, but it places an upper bound on this. And so, if you were to kind of just put this out and think about truly kind of maximum upper bounds, you would come to the conclusion that the maximum gain had to be less than 2 times VDD divided by VOV. And if we use kind of numbers that are pretty typical for us right now, VDD in our case is about 1.8 volts. VOV, we're trying to stay above 150 millivolts. Let's call it 200 millivolts. And so I would have 3.6 volts divided by 0.2. Not a lot of gain, 18 from this particular stage. The reason why I like to think about this is because it's going to set up how we approach this problem and more mathematical ways to derive this. Really where this came from, this upper bound, was the fact that both the gain, that is the small signal gain, and the DC biasing were dependent on that resistor, that R value. And these have somewhat conflicting arguments here. I want a large resistance in order to increase the gain, yet I want a small resistance to make sure that that device is still in saturation and that it's not getting pushed into triode. And so clearly these two, it's impossible to satisfy both of them simultaneously. And whether or not this is really a big problem depends on the circuit, of course, and how we're trying to use it. But I use this as more of a thought experiment of how we would approach this and what are some upper bounds. And another way to do this that you've probably seen is to use what's called load lines. And so we're going to start looking at load lines right now and try that approach. So if I was to take this exact same circuit and I wanted to construct the load line simply shows the output voltage on the x-axis and the current on the y-axis. Okay, and so the current here is simply equal to the voltage drop across this resistor, or VDD minus V out, divided by the resistance. On this x-axis, we hit the intercept of VDD. That is to say that when there is no current through this device, when I is equal to 0, there's no voltage drop, and so the output is equal to VDD. So this is pinned here at VDD. And then on the x-axis here, when Vout is equal to 0, this current is equal to VDD divided by R. Now if we take and we look at the IV characteristic of the transistor itself, the transistor has an IV characteristic where it's in triode, and then we get into saturation here, and I'm neglecting channel length modulation, so this is perfectly flat and independent of the output voltage. And so the idea is that I'm biased somewhere along here, and any perturbation in my input voltage, my small scale voltage, results in a perturbation, small signal perturbation of the output current of ID. And so if I put these two plots together, now what you can see is where they intersect, this is the operating point of the device. Okay, so with this particular value of R, this is where the transistor is going to have a DC operating point, and then any change on the input is going to move us this way or this way on our load line. And so that's how we're getting gain out of the circuit. And so the gain is really the movement across this region while we have the DC operating point set here. And so the output swings, or the output voltage swing, is how much we move on the horizontal axis here. And so you can see that for different resistances, we move around, in particular, this point on the plot. So we don't change where it intercepts the x-axis. This is always set at VDD. However, for a smaller resistance, R small, we're going to have more current, and so we will have a higher intercept point here. For a large resistance, we're going to have less current, and so this will move down. You can also see what this is doing to our gain at these different stages. So if you look at the output swing here versus for this line, the small resistance has less difference between these two intercept points compared to this, which would simply say that it has smaller gain. And so we can graphically verify, our equation that we were showing earlier. The problem with this, and this is where I was trying to lead us earlier, is really that we're pinned down here at 0. That I can't ever move this. I can move this up and down a little bit, but I'm always stuck at this point of VDD 0. And so, there's a few ways that one might try to address this. I could use a larger supply voltage. Oftentimes I'm limited by the technology, and so this won't allow me to increase VDD arbitrarily. I can increase R to a certain degree. However, I still have to keep that transistor in saturation, and so there's limits on how large R can be. Alternatively, another way of looking at this is, what if I change my load network? And what I mean by that is, instead of just using a resistor, what if I decouple it? What if I use a resistor and I use a DC bias current? Okay, and so the idea is rather straightforward. This current source here is going to set the DC operating current of the transistor, and this resistance here is going to be a small signal load. Okay, and if I set VB equal to Vout, then in the DC biasing case, none of this current will flow back up through this resistor. I will essentially have no voltage drop across this resistor. All of this current will flow into the MOSFET. And then when we're looking at small signal model, we're going to get the output impedance, or this resistance, without having to worry about this current source. And so if we were to relate this back to our load line, what this means is that I go from being pinned down here at VDD to arbitrarily being able to move up. And this is really because I'm using this now to set my DC bias point, and this to set my gain. Whereas in the previous case, I was using just this resistor to set both of them. And so essentially what I'm doing is decoupling this problem. All right, so let's look at what would happen if we had a couple of different cases here. I'm showing still this resistor with the dotted line, and now what we have is we have a case where I no longer have to have this intercept at VDD because I'm using a current bias source. And so what this means is that there are many different values that have this DC operating point that let me change the resistance independently now. And so I can increase the gain considerably without ever having to change the DC operating point, which is what I could not do with just a resistor. And so, logically, if we're thinking about this and thinking through this, one might be tempted to say that, well, now we should be able to have infinite gain. Can we ever have an arbitrarily large or an infinitely large resistor and push the gain close to infinity? Turns out that you can't actually do this for a couple of reasons, one of which is that the transistor itself has some finite DI dVDS. We talked about this back in lecture 1 and 2. This is essentially the output impedance of the transistor. And we're going to come back and revisit this a little bit later and really drill into this. Another fundamental reason, which we'll talk about a little bit later in this course as well, is that what if we had some mismatch? And when I say mismatch, what if IB and the current that was coming through this transistor that we had biased it with its voltage out here, what if there was a little mismatch in them? Let's take a look at this and let's look at it on the load line perspective and try to understand the implications. All right, so here I'm plotting a couple of different points. This would be the ideal operating point for the current that I expect. As you can see, we've cranked up the gain here such that we get quite a bit of swing for a little input variation. We have very high output variation, which means we have high gain. If, however, this operating point was to increase just a little bit, let's call it 10%, you can see that now we've moved the operating point pretty considerably given a very small change in this input bias current. You may argue that moving to the right on this is not so bad, although we are getting very close to VDD here, and so we would have clipping or large signal distortion. Alternatively, if we were 10% lower in our bias current, you can see that we come down here and we're dangerously close to operating this transistor in triode, where we're not going to have the behavior that we want. We're going to get substantially less transconductance, and it's no longer going to act like a voltage-controlled current source. It will act more like a voltage-controlled resistor. And so the point of this is that, even a very small change in this bias current with very high gain can move around the operating point considerably. And you can even come up with cases where there's no interception between these two lines. If I had a almost perfectly flat load line where I wanted to crank up the resistance to near infinity and it didn't intersect, there's no point where these two lines intersect, and this will not find an operating point. And so this is what I like to say, that we were trying to balance marbles on the tip of the cone. We want to make sure that we don't put designs into places where they are simply never going to work or only work in simulation. And this will become a little bit more important when we start talking about mismatch and other variation, in particular process, voltage, or temperature variation, and what that can do to our circuits. That is not to say that there are not solutions to this. One of the ways that you've probably seen, if you've ever seen the inverted pendulum problem, it looks unsolvable when you have an inverted pendulum just laying there. However, if you put feedback around it, you find out that you can actually balance this pendulum upside down, which seems rather strange. We could apply the same context here and that is that if I had a way to monitor the output voltage and feedback or adjust the bias current, I could move the operating point up or down to make sure that it always intersected those curves. We'll talk about feedback a little bit later on in this course as well. All right, so this brings back this question of gain. How much gain could we get? And let's just now pretend that we were able to magically bias the circuit such that ID was equal to IB, maybe using feedback, and I let my resistance, my load, go to infinity. It turns out that in this case, the gain of the circuit is still finite, and it's equal to what's called the intrinsic gain of the transistor. The intrinsic gain is really what we're getting at when we talk about the finite VDS, or finite DVDS, or the output impedance of this transistor. And so if we look at the load line that properly models this, where we no longer have this being perfectly flat, but now we have some finite slope to this, you can see where this gain comes in, is that even if I had a perfect load line, a flat load line here, there is still some finite gain. I don't have infinite gain along this x-axis here, and this is really due to the slope of this curve, is that my transistor has some finite output impedance, and when I use the transconductance, it's getting reflected back into a current through the finite output impedance of this device. So let's talk about the finite output impedance, or DID DVDS. This is really caused by a couple of different phenomena. One of them we talked about a couple of lectures ago in terms of channel length modulation. There's also other factors in modern MOSFETs as we scale down the dimensions. Drain-induced barrier lowering, it happens to be one of these other short channel effects that can also cause this, or the substrate current induced body effect, SCBE. These are really difficult things to model, and if you look at the way that they're handled in modern MOSFETs, there's dozens of parameters that are used in order to try to capture this behavior. So these parameters, these models are in what's called BSIM4 or PSP models. These are very complicated models with a lot of parameters, often empirically tuned based on measurements. So coming back to what we want to do in ECE 164, we're only going to treat this through what I'll call a first order treatment. We're only going to consider this from the classical channel length modulation effect in order to construct a manageable model that contains really the relevant feature that I want to focus on, and that's this finite slope of the output current, without getting too into these device physics. All right, so if you recall channel length modulation, essentially what's happening is that if we have a MOSFET, and we would typically define the channel length as being y is equal to 0 here, moving all the way to the drain side where y is equal to L. As we start to apply a voltage, we push this pinch-off point back towards the source due to the depletion region. This is simply p-n junction that's happening right here. Okay? And as I continue to increase this voltage, the pinch-off point moves farther and farther away from the drain, effectively looking like this channel is now shorter than it was before. And it's shorter by this amount, delta L, okay? Where delta L is a strong function of VDS. And so if we were to try to put this into our equation that we derived, where we had the drain current was equal to 1/2 mu n Cox W over L times VGS minus VT squared, now I take my L as my effective length, where my effective length is L minus the delta L that's due to this channel length modulation parameter. If I do a little bit of math on this and I factor out this L term, and then I apply a Taylor series expansion to this, I arrive at this equation right here, where I have my ideal MOSFET, And then I have this error term, this 1 plus delta L VDS divided by L. And this, we will often call this delta L over L. This is our lambda term. Okay, and so this is where we get this expression that has this lambda or VDS dependence on the DC operating point. Okay, so a couple of things about lambda. It is a single parameter that tries to capture this output impedance or this finite slope. It is inversely proportional to the channel length, which should make sense intuitively. If I have a very, very long channel, I'm not pushing it back nearly as much proportionally as if I had a very short channel. The effect of pushing that channel back is much more significant. And so this lambda is a function of the channel length. And to give you kind of typical numbers, again, I can't give exact numbers due to the non-disclosure agreement that we have in place. This is a reasonably good approximation, and it's something that you should look at and simulate and extract from our models. Okay. There are a few things that are really important to remember about this. This lambda term is really a fudge factor that helps us take into account this behavior. If you recall back, we said that it depends on many different parameters, yet we here are treating it as if it's just due to one parameter. It's useful in the sense that it gives us some kind of boundary, but we should always be careful that it's not a precise number. And more importantly, when we're talking about DC biasing, you never ever want to rely on a very precise value of lambda in order to establish the operating point. A typical rule of thumb is that if lambda were to change by plus or minus 50%, your circuit still should be able to find an operating point. And if it can't, then you probably need to rethink the architecture or redesign the circuit at a better operating point, because lambda can vary pretty dramatically. All right, so from a small signal perspective, what we have is that this finite slope is really giving rise to a conductance. It's giving rise to what we'll call GDS, which is the drain to source conductance, or inversely R out, which is 1 over GDS. And so if I wanted to mathematically prove this idea of the small signal model, I would take the derivative of the large signal IV curve, so di dVds, at the particular operating point. So here I'm setting VDS is equal to the DC operating point of VDS. And what I find is that my GDS is equal to ID times lambda, okay? Where I again can come back to this expression with VDS, and I get that GDS is approximately equal to lambda times ID. Okay, and so again, we're just taking the Taylor expansion of this expression. Okay, the approximation that we're making here is that the channel length is rather long, and so that lets us say that this last term is effectively 1. And so in the denominator, we simply have lambda ID over 1, that this goes to 0. So how good is this? Well, this approximation tends to overestimate GDS, which is typically a reasonably good thing. I would rather have a little bit of margin and know that I have margin in that. All right, so if we think about our small signal model, we started off with just this transconductor, that a transistor has transconductance, that's its primary purpose. And now we've added this finite output impedance, which looks like a resistor between the drain and the source, where GM is equal to 2ID over VOV, or if we plug in ID, we have this expression, and GDS is equal to lambda times ID. All right, so let's look at a circuit that has this, and let's do a problem here where now I have biased this with my my load, and we're going to see that this looks a lot like a transistor very soon. So this is not some contrived um, network here. This is a realistic network. And if I was to draw the small signal model of this, this transistor has a transconductance, GM times VI. It has an output impedance, R0. And then when I look up into this network from a small signal perspective, looking into this DC current source, I see an infinite impedance, so that's an open circuit. And looking into this resistance, I see R, and VB is a short, an AC short, so this is ground. And so the R0 and the R end up in parallel here. And so if I was to write the gain, that is, if I wiggle this input voltage, how much does the output voltage wiggle? It's equal to the transconductance times my input. And this current gets dumped into the parallel impedance of these two resistors. So R parallel R0. And so if we think about this idea of letting R go to infinity, right, we would find that the intrinsic gain, or the gain of the circuit, was equal to GM R out, or GM over GDS. This is what we call the intrinsic gain. This is the maximum gain that I can get from an ideally loaded transistor with a perfect current source. Okay? And so, typical numbers for different technologies, obviously this is a function of channel length. 0.18 micron, an intrinsic gain should be on the order of about 100. 65 nanometer technology is going to be more like a gain of 40. And then once you get down to very low technology nodes, things like 22 nanometer and below, intrinsic gains are on the order of 10. I mean, they're single digit type numbers. So why do we care about this? Why do we care about the intrinsic gain or this GM-R0 product? If you've ever used an op-amp, you often have very high open loop gain. And when I mean open loop gain, typical gain numbers for amplifiers are on the order of 60, 80, 100, maybe even 120 dB. And so it's a little interesting to think about, in some of these new technology nodes, how would you make 120 dB or even 60 dB for that matter, 1,000, with transistors that had a gain of 10? And so it requires quite a bit of effort to get high gain amplifiers for precision circuits in very new technology nodes. You often use them in reference circuits, and so we'll see some examples of this. We want to make currents that are independent of voltage, and this relies on us having very large output impedance. And there will be a few other examples where we'll talk about the importance of intrinsic gain later on. All right, so let's look at another effect again that we revisited back in lecture 2, and that's the backgate. So the idea here was that if I have a transistor and I'm applying a gate to source voltage, and now I'm applying a voltage between the source and the body, that is VSB is greater than 0, what happens is that I'm creating a depletion region. And so I'm pre-depleting this channel here, and what this does is this increases the negative fixed charge that I have in this channel. Okay, and this is going to repel all of the electrons that I'm trying to bring up to the surface in order to invert this channel and turn this P-type substrate to an N-type. And so effectively what I've done is I've made it harder to turn on this transistor, and so I have to apply more VGS than if I didn't have VSB greater than 0, if I had it equal to 0. And so the way that we would model this is by a change in the threshold voltage or a change in VT, where we can write that the threshold voltage is equal to the threshold voltage with 0 voltage applied times gamma, a technology parameter, the work function, and the source to body voltage. Okay? However, if you think about this for a second, a change in VT for a fixed VGS also looks like a change in the drain current. And so what we need to do is we need to derive a transconductance. Okay, and so we're going to call this GMB, where B is for the body or bulk. And what we're going to do is we're going to differentiate ID, the drain current, with respect to VBS. Okay? And so if you look at this expression here, at first glance it doesn't really have a dependence on VBS. However, recall that this VT term here does depend on the source to body voltage. And so we need to substitute this into VT, carry out this derivative, and what we'll find is that we're going to get that the transconductance is approximately equal to gamma GM divided by 2 times the work function plus VSB. Okay? What this means is that this factor here, this gamma divided by all of the stuff in the denominator, it's always going to be less than 1. Okay, and so what this means is that yes, we could use the body or the backgate of the transistor as another transconductance. However, it's only going to be 1/3 to 1/5 as good as GM. Okay, and so this is defined by this parameter here, chi, which is the ratio of GMB divided by GM. This is a pretty standard relationship that holds across a lot of different technology nodes. All right, so now our small signal model, we have the transconductor that we want, we have the finite output impedance, and we just added another transconductor here where this is equal to GMB times VBS, where VBS is the voltage that we're applying between the body and the source. All right, so now we're going to switch gears and we're going to talk a little bit about some of the capacitances that we have in these devices. We're going to divide the capacitances up into two categories, what are known as the intrinsic capacitances and the extrinsic capacitances. The intrinsic capacitance, these are capacitances that are fundamental to how the device operates, and they are independent of how we would make the device. Okay? The extrinsic capacitances, on the other hand, these are capacitances that we would call parasitic or unwanted capacitances that are there because of how we made the device. And this will become very clear when we actually start to draw out the device. Importantly, we also need to recall that the transistor is going to have different capacitance based on the operating point. And so, two very simple cases are when the transistor is on and when the transistor is off. And so we're going to walk through and look at some of these in detail. All right, so when we have the transistor in triode, that essentially means that we've formed a conductive channel between the source and between the drain. And this channel effectively is acting like a conductor here, and so we're shielding some of the capacitances. Okay? And so we have a capacitance that is between the gate and this channel, and we're going to call this CGC, capacitance gate to channel. And then we have a capacitance down here that's from the channel to the body. Okay? This capacitance CGC, it's simply equal to a parallel plate capacitance, where I have the width of the gate times the length of the gate times the permittivity divided by the oxide thickness. So this is just equal to WL times C ox. Okay? There is a little bit of a nuance here in the sense that if I wanted to divide this up, this capacitance, it's really a distributed capacitance. If I was to draw this, there's really a whole bunch of little tiny capacitors that are all linearly spaced along this channel. In the idea of bulk kind of modeling this, though, the simplest thing that we can do is just divide equally the capacitance between the source and the drain. And so that is to say that half of the capacitance will go from the source to the gate, and the other half of the capacitance will go from the gate to the drain. Now note, this is a relatively straightforward thing to do here, in part because we're in triode, which means that we have a linear and a rectangularly shaped channel. This other capacitance, this channel to body capacitance, we're going to calculate this in just a second. It's really due to the depletion region that's being formed here between the channel and the body. When the channel is on, it's usually negligible, especially relative to this parallel plate capacitance that I have sitting up here. And so we usually won't deal with this much. But there was a question asked about the CCB, and I hope that this clears it up. All right, now once we move into saturation, we have a slightly different case. And that is that now we have a triangularly shaped channel. Okay, and so this effectively means that that bottom plate of the capacitance, it doesn't change uniformly. Okay, we have to drop the voltage in a non-uniform way across the channel. And so if we were to revisit our calculations using the geometry of the channel as triangular rather than rectangular, what this would show us is that the gate to source capacitance is 2/3 times WLCox, and that there's no capacitance between the gate and the drain. So in saturation, all of the capacitance goes to CGS, but it is 33% smaller than the total capacitance that we would see in triode. If you really want to do this weekend, you can write the charge in the channel as a function of voltage and integrate from 0 to L, and you will be able to prove this kind of capacitance. It's a rather straightforward derivation. And then if we think about our long channel model of this, as I said, the drain voltage doesn't really affect the channel charge. And so this means that we don't have any capacitance for CGD in saturation. Now, of course, there are going to be second order and extrinsic capacitances that we'll talk about in just a second. All right, now for completeness, if we think about what happens when the transistor is off, okay? When the transistor is off, I have not formed an inversion layer here, and so I have no conductive channel like we saw previously. And so now what I see is effectively two capacitors that are in series. Okay, I see this gate to channel capacitance, and then I see the channel to body capacitance without this kind of conductive shield protecting it in the middle. And so I would simply calculate these two values, CGC and CCB, and then I would find the series capacitance. This CCB, it's a depletion capacitance, and so we need to know the voltage in order to calculate the depletion width. You can also, move around exactly how much depletion I have depending on the voltage, and with a large negative voltage bias, this capacitance will essentially go very small, and so the total capacitance will simply approach CGC. All right, so to summarize, the intrinsic capacitances of the device in subthreshold or in cutoff, I have no CGS, no CGD, and my gate to body capacitance is equal to 1 over CCB, where CCB is defined as the parallel plate capacitance here with this diffusion width, and WL times Cox, or the gate capacitance. In triode, I divide up this gate capacitance equally between the gate and source and gate and drain. They each get 1/2 WL Cox. In saturation, Um, the entirety of this oxide capacitance goes towards the input, whereas the drain and the body get none of this capacitance. Now coming back to why this is intrinsic, if we think about how a MOSFET works, the entire principle of a MOSFET is that I use the gate in order to control the mobile charge in the channel. So that's why this gate oxide capacitance is fundamental to the device operation of a MOSFET. I cannot build a MOSFET without having this capacitance. All right, so there's another, we've talked about the intrinsic gain of the device. There's another metric that's often used to describe transistors, and that's how fast a transistor is. This is what's known as the transit frequency, or FT, of a device, and it's defined where the transistor has unity current gain of a common source transistor. Okay? And so the idea is that if I put a current into this transistor, I want to short the output and measure the output current. And obviously the circuit is not biased properly. I'm showing simply the small signal equivalent of it. If you work through the math, you can prove that Ft, or omega t, is equal to Gm over CGS, where it's dependent on these technology parameters, okay? And we're neglecting extrinsic capacitance here. And so there's a couple of things, this 3/2 prefactor, this really just comes from CGS and saturation. Mu, if I increase the mobility, or how quickly I can move the electrons from the drain to the source, that makes sense that the transit frequency should be linearly dependent on that. Increasing the overdrive voltage also makes sense. And then decreasing the channel length. So this is where transistors, as we've shrunk the channel length, have gotten considerably faster. Shorter L means that we have a shorter path. We don't need the transistors or the charge carriers to move as far. And so that results in a much, much faster device. There are a few things about the transit frequency that we need to keep in mind. One, this really does not accurately predict how fast we could use this device. Very much like the intrinsic gain, it's a ideological parameter that describes this technology. You couldn't operate a transistor to get the intrinsic gain out, in part because you could never make a perfect current source, and in the same way we could never operate this transistor all the way up to Ft, because we could never not load it with any additional capacitance. And the capacitance that we're describing here is a lumped model where the capacitance is all taken at the input, CGS, whereas really if you were to start to think about this and draw it out, it's really distributed. And that's that along the drain to source channel, there's a bunch of really small capacitors that in total add up to CGS, but you would not be able to treat them as a simple lumped model. And so if you're taking 166, you will see this many times over again. The general rule of thumb is that you typically can use the lumped model up to about Ft over 5. And it's often hard to design circuits, any circuit, even simple circuits, that approach Ft over 20 or Ft over 50. So that kind of gives you a generally idea of, is this technology fast enough for the circuit that I want to build? All right, so now let's revisit some of these extrinsic capacitances. There's a couple of extrinsic capacitances that are pretty obvious. When we make this gate oxide on top of the transistor, we overlap the source and we overlap the drain. We do this to ensure that we're able to invert this entire channel. Okay? And so what that means is that this overlap is going to give rise to a capacitance. This is known as the overlap capacitance. It directly adds to the CGS and CGG that we already are going to have there. In addition to that, we have depletion capacitance from the source and from the drain, towards the body. These are very much like we were talking about the channel capacitance. These are dependent on the voltages. These are just reverse bias diode capacitance. All right, so this overlap capacitance, it's simply equal to the width of the overlap times Cox. However, if you look at kind of the 3D geometry of this, you quickly realize that in addition to this direct overlap capacitance, there's a lot of fringing electric fields that are coming off of this due to the asymmetry in the height, that it's a very tall device. And so this fringe field can actually be a very significant portion of the overall capacitance. Our back of the envelope model that we'll use is simply that the overlap capacitance is equal to COV prime, where COV prime is roughly half a femtofarad per micron times the width of the device. And that's the width is the width into the plane in this figure. All right, to calculate the junction capacitance, we need a couple of parameters. We need to know the area, and we need to know the perimeter or the edge of the device. And so if we look at a transistor shown over here, this is the drain, this is a diffusion, this is the source, this is a diffusion, and then I have a poly gate that's sitting on top. And so the length of the gate, that's L. This length over here, this is the diffusion length, typically the minimum that I need to make for this device. It's often a multiplier of the lithography limit. Typically a rule of thumb is 3 is decent. And so I can calculate the area of this now. The area of the source, that's simply equal to this diffusion, L diff, times the width of the device. So that's AS is equal to W times L diff. The perimeter is simply equal to the width times 2 of the lengths. Okay? And you may ask, why don't I have typical perimeter? Why don't I count this other width? And the reason being that recall that we're inverting the channel. We're turning it on. And so this is actually a conductive path over here. So we're inverting the material to try to have a ohmic contact between the source and the drain. And so we're only considering this side of the width when we consider the perimeter. The exact same equations apply over here towards the drain. And then I can use the diode equation for a reverse bias capacitance in order to calculate what the total junction capacitance, CJDB and CJSB. So we calculated AD. This is the junction capacitance coefficient. This is the sidewall of the junction capacitance coefficient. MJ and MJSW, these are related to the doping profile for the bottom plate as well as the sidewall of the capacitance. And of course, these are strongly dependent on the voltage that we apply towards VDB as well as VSB. All right, so now if we add these into our table of capacitors, you'll see that in subthreshold, we've added these overlap capacitances here. In triode and saturation, similarly, we've added the overlap capacitance. We now have a capacitance between the source in the body and the drain in the body. This is our junction capacitance. In the exact same way that we had the capacitance divided equally for the gate capacitance, we also have the channel to body capacitance. However, relative to CJSB and CJDB, this capacitance is typically very small, and so we'll typically neglect it. Same is true in saturation for exactly the same reason, that we end up with 2/3 due to the channel geometry, just like we had for CGS. All right, so now if we look at our small signal model, it's starting to become a little bit more complicated. We've added the capacitances, namely we've added this gate to drain capacitance, gate to source capacitance, gate to body capacitance, source to body, and then drain to body, in addition to the 2 transconductors that we had and the finite output impedance. All right, so now I want to talk a little bit about the body connection, in particular where we're going to tie the bulk. And so transistors are not really 3-terminal devices like we often describe them as. We always have to remember that there's this back gate or body contact that we need to do something with. So transistors are 4-terminal devices. And so you'll recall that for an NMOS, all of the NMOS sit in the same P substrate. And so what that means is that I can't isolate the body connection. And so I'm always going to tie the NMOS body to the lowest potential. The PMOS device, I have to put this inside of an N well and then make ohmic contact to that well. So that's this N plus diffusion right here. And so this means that now I have freedom for a PMOS of where I want to tie the body. I could tie the body directly to the source, or I could tie it to VDD or any other arbitrary voltage that I wanted, provided that it was higher than the source voltage. There are some technologies that allow you to do the same kind of thing as we did for a PMOS, but you do it for an NMOS. Instead of one well, we now have a second well where we have to put this into a P well and then an N well. In order to get back to having a P-type substrate. And so that's what's known as a triple well technology. Here you would say you have 2 wells, that adds the 3rd well. All right, so if we look at different ways of connecting the body, for an NMOS, it's very simple. We really don't have a choice. The body is always going to be tied to VSS or ground. For a PMOS, we have the ability to tie it to the source, or we can connect it to VDD or another arbitrary voltage if we wanted to. There are some implications of this, though, one of which is that depending on where we connect the body, we can add an additional capacitance term to our small signal model. And so if you were to look at the cross-section again, you'll see very quickly that there's another reverse bias diode here, and that's from my P sub to my well. I have a PN junction, which I'm keeping reverse biased, and that means that I have a capacitance here. I have a depletion region, and so depending on where I tie this N well, if I tie it to the source, then I'm going to see this additional capacitance. If I instead tie this just to VDD, then it looks like I have capacitance between VDD and substrate or ground, which is typically not a big deal. In fact, it's usually good to have decoupling capacitance there. The one thing to keep in mind is that this is very dependent on the layout of the device, and so when you're simulating this, you have to manually add this capacitance. There's no way for the simulator to know how big you are going to make this well at design time. So you have to add this diode manually in order to capture this capacitance. All right, in order to illustrate that, we can look at the layout here. Again, source, drain, diffusion, and I'm showing you contacts that we're making to these diffusions. This is the gate. And in addition to that, now I've added another diffusion over here. This is sitting inside of a N well, and so this is an N plus diffusion. This is P diffusion, and we're making contact to our well over here. Okay? And so the question is, if we wanted to calculate the area of the well, how would we do this calculation? And so the calculation is rather straightforward. If we look at the area of the well, it's minimally equal to this diffusion length, 2L diff. Okay? That's simply these two right here, plus the channel length, okay, L, plus I have to have some distance between the edge of the well and my device. Okay? And then I have to have distance between these two diffusion regions such that they don't overlap. and this we're going to call x2. And so I end up with 2x1 plus x2, and all of this is times the width of the device, plus the dimension that I need from the edge of the well contact on both sides, and so 2x1. And so, if we just took a very simple device to kind of give us some rough order of magnitude numbers, let's say that I had a 10 micron over 1 micron device, and that in this particular technology, x1 was equal to 5 micron and x2 was equal to 3 micron. I could put all this together, and I would calculate that the total area, the minimum area of the well was 400 microns squared. And this is not nothing, especially considering that the device itself is only 10 square micron. We have quite a bit of overhead here just due to all of the spacing constraints. And so this capacitance can actually be quite significant and can limit your performance. And so you have to think very carefully of whether or not it's worth dealing with the body effect and having the body tied to VDD, or if you really want to get rid of the body effect and tie this to the source, you're going to pay the price in terms of this capacitance. All right, so what does our small signal model look like when we add this? We add one more capacitance over here for a PMOS, and this is only in a PMOS where we have this body to substrate capacitance, where substrate is the actual VDD or VSS of the device, the substrate that we're implanting all of this material into. Okay, with that, we've covered the entire small signal model, and we now have a very complete small signal model that we will use moving forward. One thing that I would like to point out about this model is that it looks very complicated. We've added 1, 2, 3, 4, 5, 6 potentially capacitors, an output resistance, and an additional transconductance. We're going to get very good at understanding what parameters we need to keep and what parameters we can make first order approximations with and not worry about. I would say that this GM we're always going to keep track of, CGS we're almost always going to keep track of, and CGD is almost always important. To a less degree, CJB, CSB, CDB typically are not that relevant. They're going to be small compared to other capacitances that are already in the circuit. And GMB, we often will not try to use the body as a transconductor, and so we usually won't try to put AC signals in here as well. And depending on how we connect up this body. And so fundamentally, the most important ones in most circuits are GM, CGS, R out, and sometimes CGD. All right, have a good day. Thank you.